All right, let's look at 3.3, Littlewood's three principles, Egoroff's theorem, and Lusin's theorem. The plan here is to review one result we had from the past and kind of elaborate on what we mean by the term nearly. We're never going to formally tie down exactly what we mean by the term nearly, as we did when we talked about almost everywhere. We had very specific definition for what almost everywhere means. We throw away a set of measure 0. Nearly, crudely put, means we're ignoring the behavior of whatever function sets on a set of small measure. We'll let epsilon be greater than 0, and we're throwing out a set of measure less than epsilon. That's what nearly means, roughly put. On page 64 of Royden and Fitzpatrick, they make three informal statements with this idea of nearly in terms of throwing away a set of small measure. They say every measurable set is nearly a finite union of intervals. Every measurable function is nearly continuous, and every convergent sequence of measurable functions is nearly uniformly convergent. These are called Littlewood's three principles. More of the history in a second. This first result deals with measurable sets. We actually saw this in section 2.4, outer and inner approximation of Lebesgue sets, Lebesgue measurable sets. And we saw it in Theorem 212. And even use the word nearly at that stage as well, foreshadowing what we're doing right now. In fact, the specific statement was, if E is measurable with finite outer measure, then for every epsilon greater than 0, there is a finite disjoint collection of open intervals, I1 through I sub n, for which, if we define set O to be the union of those intervals, then we get the outer measure of the symmetric difference of measurable set E and open set O to be less than epsilon. Symmetric difference, recall, was E set minus O plus O set minus E, the stuff in E that's not in O and the stuff in O that's not in E. We could deal with this exclusively in terms of measure instead of outer measure. You're told E is measurable, you know, open sets are measurable. Maybe at this stage we didn't have quite all that information, but anyhow, we could write this in terms of measures instead of outer measures. And so what you're saying is, where set E and set O agree, that is where they have common elements, the intersection of E with set O, that that's the big set. We're looking at the complement of that set with respect to E union O. So we've got E intersect O agreeing everywhere except here. That is, they have the same elements except here. And here, the symmetric difference has a small measure. You give me epsilon, I maybe choose a new collection of open intervals. But anyhow, we are approximating this measurable set in this sense with an open set. And not just any open set. I think the impressive word is an open set consisting of a finite disjoint collection of open intervals. This is the only time we'll use symmetric difference in this conversation based on the Littlewood's three principles. This we proved back in section 2.4, so this is sort of water under the bridge. This was talking about nearly in this setting of measurable sets. Back to section 3.3, the other two claims deal with sort of the topic at hand now, which is measurable functions, and saying every measurable function is nearly continuous and a convergent sequence of measurable functions is nearly uniformly convergent. And what we'll do in these two is we will throw out a set of measure epsilon. There won't be any of the symmetric difference stuff involved. But this allows us, in some sense, to approximate measurable functions and sequences of measurable functions in certain ways. As I commented, these are called Littlewood's three principles after John Edensor Littlewood. Little history on Littlewood. Almost all of Littlewood's mathematical research was in classical analysis, but in this area, he looked at a remarkable range of subjects, and he used an even broader range of techniques in proving his results. For 35 years, he collaborated with G.H. Hardy, working on theory of series, the Riemann zeta function, inequalities, and the theory of functions. The Hardy-Littlewood collaboration is one of the famous collaborations in math. Littlewood's actually in my mathematical genealogy. My PhD advisor, trace that back 6 generations, and Littlewood's there. I did classical complex analysis, and this theory of functions and Riemann zeta stuff sort of suggests that he was active in complex analysis as well. At one point in his graduate school career, Littlewood's PhD advisor, E.W. Barnes, gave him the problem of proving the Riemann conjecture, the Riemann hypothesis, concerning the location of the zeros of the Riemann zeta function. So that's still probably the most famous unproven math conjecture concerning the location of the zeros of the Riemann zeta function. So bad dissertation problem. This was probably 100 odd years ago. Still remains unproved, so I'm sure things had to change, and Littlewood had to get a different PhD problem, says he's not solving that. Here's a photo of him. This information coming from St. Andrews University, Mac Tudor History of Maths archives. I've mentioned it several times. Good place to go for history of math stuff that's reasonably technical. Let's formalize these a little bit more. Littlewood's 3 principles say, well, we actually looked at Theorem 212. Littlewood's first principle deals with measurable sets of finite outer measure in this approximation by finite collections of open intervals. Let's sort of let that one lie and concentrate more on the second 2. The second of Littlewood's 3 principles is also called Lusin's theorem, and says, let f be a real valued measurable function on set E. Then for each epsilon greater than 0, there's a continuous function g on the reals, defined on all the reals, and a closed set capital F contained in E, for which function lowercase f equals that continuous function g on set capital F, and the measure of E set minus capital F is less than epsilon. So we're getting this real valued measurable function to equal a continuous function everywhere except a set of small measure. Where function f is defined, that is its domain capital E, we've got f and g, function f and continuous function g equal to each other except on this set E set minus capital F, a set which can be made arbitrarily small, not 0, in measure. In other words, a real valued measurable function is nearly continuous in this sense. Littlewood's second principle will actually prove this one third. We're going to prove this one using the following. Littlewood's third principle, also called Egoroff's theorem, says assume E, set E has finite measure. Let f sub n be a sequence of measurable functions on set E that converges pointwise on E to real valued function f. Then for every epsilon greater than 0, there's a closed set capital F contained in E for which f sub n converges to f uniformly on set capital F, and the measure of E set minus capital F is less than epsilon. So they're saying if, in the setting of measurable functions, if you have pointwise convergence on set E, it means at every point of set E, pointwise convergence on set E, then if you'll throw out just a little bitty set, E set minus F, then you can actually get uniform convergence. And not just any set they're throwing, any set on which they're getting the uniform convergence, but a closed set. So it's more than measurable, it's a closed set. So that's a little bit of an extra constraint there. So again, these three principles involve roughly an idea of except on a set of measure epsilon. That's the idea behind the nearly. And we've stated these earlier informally, but there's a restatement, still a bit informal. We never define nearly. The first result actually dealt with a symmetric difference, whereas the other two dealt with E set minus F, throwing out a subset, and not looking at any sort of symmetric difference stuff in the latter two. There's some similar results. The problems from section 3.2, problems 16, 17, and 18 deal with an idea of simple functions, characteristic functions, and a nearly kind of behavior. Paraphrasing what those say, a characteristic function on a bounded measurable set is nearly a step function. Problem 16 says, and that dealt with characteristic functions. Simple functions are defined in terms of characteristic functions. A simple function on a bounded measurable set is nearly a step function as well. And a bounded measurable function on a bounded measurable set is nearly a step function. So we're getting out behavior similar to step functions nearly everywhere. I guess the real punchline is you give me epsilon to play with. And this time it's a measure of a set being less than epsilon. And we can do a lot of controlled things if you'll let me throw out a set of measure epsilon. So let's look at proofs of the second and third principles of Littlewood. Let's do, as I said, let's do the third one first and the second one second. The first one we did in a previous section. So anyhow, let's do Egoroff's theorem first. The reason being we're going to use this in the proof of Lusin's theorem. So we're going to use the third principle in the proof of the second principle. All right, so first we need a preliminary lemma. Let's just go look at the lemma and the proof of Egoroff. Okay, setting is assume E has finite measure. Egoroff's theorem will be stated for sets of finite measure as well. E has finite measure. Let f sub n be a sequence of measurable functions on set E that converges pointwise on E to real valued function f. So sequence of measurable functions converging pointwise to a real valued measurable function. They say real valued means they're not allowing this limit function f to take on the value infinity, to take on extended real numbers versus just regular real numbers. The claim is for each eta greater than 0 and for each delta greater than 0, there's a measurable set, capital A, subset of set E, and an index capital N for which f sub n minus f in absolute value is less than eta on set A for all n greater than or equal to capital N, and the measure of E set minus A is less than delta. All right, this is a preliminary lemma in the proof of Egoroff's theorem. Egoroff's theorem dealt with uniform convergence. Do you see some uniform convergence here? Yeah, right there. They say we've got f sub n minus f less than eta on set A for all values of the index sufficiently large. All right, that is uniform convergence. You would see this probably in a senior level analysis class more explicitly with your hands on the x values. If you like, f sub n of x minus f of x in absolute value is less than eta for all x in set A. For all x in set A, that's the uniform part right there. So I can see where there's some use of this to uniform convergence. But they've left the x's out. They've said this behavior occurs on set A. So that means it holds for all x in set A. And that's where the uniform part's coming in. So crudely put, we're getting uniform convergence nearly everywhere on set E. This holds on set A. Set A is not all of set E. The sequence of functions are defined on set E. The limit function is defined on set E. Set E is the domain of all these functions. Yeah, we're not getting this behavior on all of set E. We're getting it on set A, and set A is close to set E in this sense. The measure of E set minus A is less than delta for all eta and for all delta. All right, so let's prove that. First off, when we look at the absolute value of f minus f sub k, or f of x minus f of k, sorry, f of x minus f sub k of x, absolute value. This is well defined. There's no infinity minus infinity concerns, which is a legitimate concern when you do arithmetic and you're allowing extended real numbers in. We are not for the f function. Maybe we are for the f sub n functions, but the limit function doesn't have any infinities in it. So there is no infinity minus infinity from this because the f function is never infinity. So well-defined function, f minus f sub k, absolute value of, that's a measurable function by, I guess, theorem 3.6 and proposition 3.9. Well, it's because a linear combination of measurable functions is measurable, and the absolute value of a measurable function is measurable. So linear combination, in particular, the difference. The difference is measurable, and the absolute value of that is measurable. So this thing here is a measurable set. So if we look at the x values in the domain of the functions, such that f of x minus f sub k of x, absolute value of, is less than eta, that's a measurable set for all eta, a real number. Definition of measurable. I'm using the fact that this function here, absolute value of f of x minus f sub k of x, this function here is a measurable function as we just observed. So I know that function less than any real number, call it c or eta, produces a measurable collection of x values. That's what the definition of measurable function was. Since this is a measurable function, then those are measurable sets. Okay. Define E sub n to be a set of x values from set E such that the absolute value of f of x minus f sub k of x is less than eta for all k greater than or equal to n. Okay, so there's the new part in the definition of this E sub n set. If you like, that would be an intersection of all x and e such that f of x minus f sub k of x, absolute value of, is less than eta. And notice it's the index we're looking at here. For all k greater than or equal to n, all right, well, let's define that in terms of an intersection k equals n to infinity. So saying for all k greater than or equal to n would allow us to treat that set in terms of an intersection. I bring that up because then you can see that this collection of sets, E sub n, is an ascending collection of measurable sets. I write it as an intersection. Notice n is, in a sense, the fixed index for this E sub n. It's the k's that change. If I intersect from k equals n to infinity, and then I increase n, say by 1, this gets 1 larger, then what we're going to get is an intersection of fewer sets. And when we get an intersection of fewer sets, we're getting a larger collection of x values. So indeed, this is an ascending collection. They're all measurable sets. Each of the sets here are measurable for all k, I guess is how I'd treat that. And so their intersection is measurable. We're in a sigma algebra. So define E sub n is given. The E sub n form an ascending collection of measurable sets. You know where we're going with this. As soon as we talk about ascending collections of sets, you know, continuity of measures not far behind. Now, F sub n converges pointwise to F on E. That was hypotheses. So we can write set E as the union of these E sub n's. Think of it like this. I know we've got pointwise convergence. This sequence f sub n converges to this function f, and it does it for every x value in set E. So for any k, eventually, when k is large enough, we'll have this difference less than eta. So that holds for all x and e, that eventually f of x and f sub k of x in distance is less than this parameter eta. So in other words, we can write set E as a union of all these E sub n's. When you take a union of an ascending sequence, we've defined that to be the limit of the E sub n's. Ascending sequence, the union of an ascending sequence of sets is written as a limit. The intersection of descending collection of sets is also written as a limit, but we've got the ascending collection here. So we've got set E written as the limit of the E sub n's, the sets themselves. We did define in this setting what it means to take a limit of a sequence of sets. And in continuity of measure, we related the measures as follows. Continuity of measure tells us the measure of E then is the limit of the measures of the E sub n's. We've taken the limit out of the measures, how we explained this back when we were looking at continuity of measure in this setting of ascending and descending sets. All right, so we've related the measure of E to the limit of the measures of the E sub n's. We are considering E to have finite measure, right, hypotheses in the lemma. So we can choose an index, call it capital N, such that the measure of E sub capital N is greater than the measure of E minus delta. I know eventually the measure of E gets close to, or sorry, the measure of E sub N gets close to the measure of E. How close? Well, let's say delta. So eventually, that is for some capital N, we have to have the measure of E sub capital N greater than the measure of E. Monotonicity is somewhere in here, some sort of like one-sided limit deal going on with this particular limit of numbers. But we can get within delta of the measure of E. So in particular, we can get the measure of E sub capital N to be greater than the measure of E minus delta. And if you like, it's less than the measure of E plus delta as well. It's actually less than or equal to the measure of E by monotonicity. But we can get this to hold eventually. So we're, how we doing here? We're looking for, looks like the end is near. We're looking for a set A, a measurable set. Okay, all these E sub capital N's are measurable. That's good. Such that this kind of thing occurs. And that's the kind of thing we had occurring on the E sub n's. So define capital A to be the set E sub capital N. Then we will have on that E sub capital N, we'll have F, the way we dealt with it before was F of X minus F sub K of X less than eta on that set E sub capital N, provided the index was at least capital, was this big. So we've got the kind of convergence we want from the previous slide. Defining A in this way allows us to consider the measure of E set minus A. That's the last part of it. We want that to be less than delta. Excision property says, provided you're dealing with finite measure sets, and we are by hypothesis, the measure of the set difference is the difference of the measures, and they have to be nested. A is a subset of E, we're good. The set capital A is the same as a set E sub capital N, so make that substitution there. And we just saw the measure of E minus the measure of E sub capital N is less than delta. Rearrange this little inequality here. So that gives us that the measure of E set minus A is less than delta, and that's the last part. So there you go. We've got like a uniform type of convergence on set A. Set A is a measurable set. Eta and delta could be anything. Let's prove Egoroff's theorem. We're going to pick some specific values for eta and delta there. And we're going to go beyond measurable set A to closed set F. Okay. So Egoroff's theorem says, assume E has finite measure, comment to be made later is Egoroff's theorem doesn't hold if we don't have this hypothesis. But the previous lemma had the hypothesis that E was finite measure as well. Let f sub n be a sequence of measurable functions on set E that converges pointwise on set E to real valued function f. So far, same hypotheses as the lemma. Then for each epsilon greater than 0, there's a closed set, capital F, contained in E for which f sub n converges to f uniformly on capital F, and the measure of E set minus capital F is less than epsilon. This differs from the lemma in that now we've got a closed set F that we're throwing away. In the lemma, we had a measurable set that we're throwing away. I guess also we didn't state it in terms of uniform convergence, but there was some uniform convergence in that lemma also. Okay, so let epsilon be greater than 0. Let n be any natural number. So we're fixing lowercase n for now, but it could be any natural number. The following holds for arbitrary n. Let delta be epsilon over 2 to the n plus 1, and let eta be 1 over n. We know by the lemma for any eta and delta, we had certain behaviors. That behavior was, we can get f sub k minus f in absolute value less than eta. We've chosen eta to be 1 over n on a set capital A sub n, provided the index was sufficiently large, where A sub n is a subset of E, and the measure of E set minus A sub n is less than delta. So there's the less than eta, less than delta part. The less than delta was related to the measures, the last part of the proof of the lemma. And we've chosen delta here to be epsilon over 2 to the n plus 1. Okay, that, you know, we're probably going to do something with a geometric series with this part here. This is ultimately, it's an epsilon over 2 proof. We're going to use the lemma to get half of the epsilon, and we're going to, from there, generate the closed set with the other half of the epsilon. This is ultimately an epsilon over 2 proof. Okay, so we can find A sub n, capital A sub n, a set satisfying these properties. Define capital A to be the intersection of all of these A sub n's. Then we get the measure of E set minus A. We define A to be the intersection of these A sub n's, so that'd be E set minus the intersection. De Morgan lets us rewire this a little bit from basically a complement of an intersection to a union of complements in a sense. De Morgan allows us to rewrite this intersection stuff as a union thing. The set subtraction, remember, is defined in terms of complements, so that's how De Morgan fits in. Now we've got a measure of a union. Well, we've got countable subadditivity. We can write that as less than or equal to the sum of the measures of the constituent parts. Hey, these constituent parts, the measure of E set minus A sub n, we were just talking about that. We know the measure of E set minus A sub n is less than epsilon over 2 to the n plus 1. We chose the A sub n's that way. And we can do that by the lemma. So we've got the measure of E set minus A less than or equal to this sum, and we know each of these terms is less than this. We'll pick up with that on the next slide. We're pretty close to getting the measure of this to be little, but it's not set A we're interested in. Set A is a measurable set, right? Right. Each of the A sub n's are measurable. A is a countable intersection of measurable sets. Set A is measurable. We're looking for more than a measurable set. We're looking for a closed set. Okay, so picking up here, measure of the set difference less than or equal to the sum of the measures. And each of those little sets had a measure of epsilon over 2 to the n plus 1. Sum that geometric series, you get epsilon over 2. Set A is not the set we're looking for. This is not the set you're looking for. You're looking for a closed set. Well, it's still got epsilon over 2 wiggle room to play with. All right, let's show we've got uniform convergence on this set A by letting epsilon be greater than 0 and choosing an n sub 0 such that 1 over n sub 0 is less than epsilon. All right, as we had above, we know there exists a capital N based on that epsilon, really, based on that n sub 0. such that we can make f sub k minus f an absolute value less than epsilon. Let's make it less than 1 over n sub 0 on a sub n sub 0. Actually, that's how we chose the set a sub n sub 0. Let's take a peek back at that. Provided the index is sufficiently large. So we had f sub k minus f an absolute value less than 1 over an integer on set a sub integer, provided k was greater than or equal to capital N based on that integer. Let's go back and look at that. Yeah, here it is, f sub k minus f, absolute value of less than 1 over n on a sub n, provided k was greater than or equal to some integer capital N based on that n. And something about the measures. We've taken care of the measures part. All right, so that's exactly what we have, except we're choosing this n sub 0, where n sub 0 was sufficiently large that we had 1 over n sub 0 less than epsilon. All right, so this behavior here is exactly what we had in the choice of the a sub n's. Now, a is a subset of a sub n sub 0. Remember, a was an intersection of all of the a sub n's, including whichever one n sub 0 is. We had 1 over n sub 0 less than epsilon. So we could say f sub k minus f an absolute value is less than 1 over n sub 0, and in turn is less than epsilon. So that's what we've got here. This holds on set a sub n sub 0. A is a subset of that set a sub n sub 0. So this holds also on set capital A. It's a subset of a sub n sub 0. We went sufficiently far out to get this kind of behavior, sufficiently far out in terms of the index n. So this holds on set A, provided the index is sufficiently large, the other little part here. That's uniform convergence. Just read this. Absolute value of f sub k minus f is less than epsilon on set A, provided the index k is sufficiently large. On A means for all x values in set A, and that's what uniform convergence of a sequence of functions is. You give me the epsilon, and I can find a capital N that works for all x values in set A. This capital N value works for all x values in set A. They state it as on set A, remember. So that is uniform convergence. And we've got that f sub n converges to f uniformly on set A. And from above, we had the measure of E set minus A is less than epsilon over 2. But we're still not done. If they had said there exists a measurable set such that all this stuff happens, we'd be done. They didn't want just a measurable set. They wanted a closed set. Okay, let's find that closed set. Theorem 211 told us there's a closed set F contained in a measurable set for which the measure of A set minus F is less than epsilon over 2. Let's take a peek at Theorem 211. Also in section 2.4. If I scroll up from here, we had 4 conditions equivalent to the measurability of a set, And let's see, this is the one we're using. For all epsilon greater than 0, there's a closed set F contained in E such that the outer measure of E set minus F is less than epsilon. We're doing that where the measurable set we're interested in is the set A. Remember, A is a measurable set, and we'll replace epsilon with epsilon over 2. So back to the proof. Yeah, A is measurable. So there's a closed set contained in A such that the measure of A set minus F is less than epsilon over 2. Before we had E and epsilon, man, things are different. We've got set A, it's measurable, that's all we needed. And this is greater than 0, and that's all we needed for that. So there's your A closed set. And it's the right kind of closed set. If we look at E set minus F, and that's what was dealt with, not E set minus A, but E set minus F was dealt with in the statement of Egoroff's theorem. Remember, these sets are nested. F is a subset of A, and A is a subset of E. That were nested that way. So when I write E set minus F, we can write it as E set minus A, union, disjoint union, A set minus F. This includes only things in set A. This includes nothing in set A. So there's your disjointness. This is the stuff in E that's not in A. Here, we're taking some of the stuff in A and including it, but none of the stuff in F. So on the right-hand side, indeed, we have E set minus F. You can Venn diagram your way through that if you need to, but that's a true set equality. And since we've got a disjoint union, then the measure of the difference, that is the measure of this disjoint union, can be written as the sum of the measures. No justification there. It's finite additivity. Measurable sets are finitely additive, so no issues there. And we had the measure of E set minus A less than epsilon over 2. Yeah, that was up here. We had the measure of A set minus F less than epsilon over 2. That was our choice of set F down here, less than epsilon. So we've got the measure of E set minus F less than epsilon as needed. We had F as closed set F as needed. How about the uniform convergence? You had uniform convergence on set A. You actually had uniform convergence on set A sub n sub 0. But we took A as a subset of that and had uniform convergence on set A. If I take a further subset, we've also got uniform convergence there as well. If you've got uniform convergence on a big set, then you've got uniform convergence on subsets of that set. That is, we've got uniform convergence on set capital F. So capital F is the right size with a less than epsilon. It's closed as required, and we've got the uniform convergence on that set as required. So there's your Egoroff's theorem. Okay, back to section 3.3. Egoroff's theorem, it says, assume E has finite measure. It doesn't hold in general. That is, if E is of infinite measure, Egoroff's theorem is false. You're asked to find a counterexample in one of the problems out of the book, number 27, 3.27. We can weaken the hypotheses a little bit by throwing in some almost everywheres. We could say the convergence holds almost everywhere instead of pointwise almost everywhere. And instead of saying F is real valued, we could get away with saying F is real valued almost everywhere. That's problem 28 to establish that. These are very, very weak observations that I can throw some measure zero sets here and there, and it doesn't change anything. These were claims about measures ultimately. The following is a special case of Littlewood's second principle and only applies to simple functions. We'll see Littlewood's second principle applies to measurable functions. All right, so we're going to state a special case of Lusin's theorem. So this deals with Littlewood's second principle, and then we'll prove Lusin's theorem. So I really view this as a lemma in the proof of Lusin's theorem. So we'll go through the proof of that. An observation to wrap up the section is, hey, Lusin's theorem, it holds if we weaken the hypotheses on this real valued thing to real valued almost everywhere, or finite almost everywhere. Another exercise. Again, it's pretty weak generalization. I can usually throw the almost everywheres in with abandon in a lot of this stuff, and nothing much changes. We're talking about measures of sets, I say, ultimately. Yeah, you're talking about the measures of these sets. Yeah, some things get messed up on a set of measure zero. That doesn't affect the measures of these sets. So let's look at the lemma to Lusin's theorem and the proof of Lusin's theorem. Let F be a simple function defined on set E. Then, claim is, for each epsilon greater than 0, there's a continuous function, G, defined on the reals, and a closed set, capital F, contained in E, for which F equals G on F, and the measure of E set minus F is less than epsilon. So you might read this as, in the nearly lingo, every simple function is nearly a continuous function. Right? Specifically, it means what it says, but with the nearly lingo, that would be the interpretation. All right. Well, if we've got a simple function, by definition, that was a function that took on a finite number of values, a measurable function that took on a finite number of values. Let A1 through A sub n be the values, the distinct values that the function takes on. and let E1 through E sub n be the sets on which the function takes those values. On set E1, the simple function has the value A1. On set E2, the simple function has the value A2, and so forth. In that way, since the A sub k's were distinct, then these will be disjoint sets, the E1 through E sub n. Okay, we're looking for a closed set, eh? We're looking for a closed set, capital F. Well, we were just looking at Theorem 211 that told us if you've got a measurable set, we can approximate it inside with a closed set in a certain sense. So let's take each of these E1 through E sub n's and find a closed subset, F sub k of E sub k, k equals 1 to n, such that the measure of E sub k set minus closed set F sub k is less than epsilon over n. So I'm taking a little subset F sub k of each of the E sub k's. Remember the E sub k's, they're disjoint. These F sub k's being subsets of the E sub k's correspondingly, and they'll be disjoint as well. So define capital F to be the union of the F sub k's. Okay, so here's where we are. The domain of this simple function is set capital E. We've partitioned E into these pieces, E1 through E sub k. Inside each piece, we found a little closed set F sub k. We've taken the union of those F sub k's, finite. Finite union of closed sets is closed. So F is a closed subset of set E. So we found the closed set. It's got the right topological properties. We need to check the measure properties, and we need to do something about defining this function G. All right. The E sub k's are disjoint. We made sure of that. By countable additivity, then we have the measure of E set minus F. I mean, the punchline is less than epsilon, as it should be. But set E is defined to be the union of the E sub k's, or we partitioned set E into the union of those E sub k's. The F sub k's are subsets of those. So when we take E set minus F, that's taking the union of the E sub k's set minus the union of the F sub k's, and that's how set F was defined. These are disjoint for the record, but we got this disjointness. From E sub 1, I have removed F sub 1. From E sub 2, we've removed F sub 2 and so forth. So I can write that as a disjoint union of the set differences because of the disjointness. We just get that set equality, and so the measures are the same. And we're in business here. Now we've got a measure of a disjoint union, a finite collection. Everything inside is measurable. So we've got finite additivity. We get the measure of E sub k set minus F sub k for 1 to n. We made sure those things were approximately the same size in this sense. We had the measure of E sub k set minus F sub k less than epsilon over n. So we get epsilon over n times, sum them, and you get epsilon as desired. All right, so we found set F. It's closed like it's supposed to be. It's the right size that they wanted. We're looking for function G. There is a continuous function G defined on all of R. And we'll get F equal to G, function F equal to G on set capital F. All right, so we got to deal with a continuous function G. Define G on capital F as G of X equals A sub K when X is in F sub K. Remember the F sub K's decompose. Partition's the right word. The F sub k's partition up set capital F. So any X in F is in exactly one of the F sub k. So this is well defined. So define G sub X like that on set F. All right, we want G actually defined on all of the reals. So we got a ways to go still. So I'm going to let one of the exercises take care of some of the heavy lifting. But define G on F as given. All right, the F sub k's are closed. Claim is G is continuous on F. All right, here's why. Take an X in F sub k. by taking a sufficiently small neighborhood of x, that is, taking an open interval containing x, I can choose such a little open interval that's disjoint from the other f sub k's. If this is f sub 1, say, if x is an f sub 1, then I know I can find an open interval containing x that doesn't intersect f sub 2, f sub 3, up to f sub n. Hey, remember, that's a closed set. Its complement then is open, so I know there exists an open interval containing x disjoint from that closed set. Now, on this little open interval, we've got that function being, the function g being constant, well, on the open interval that intersects set capital F where the function's defined. So we've got continuity of this function on set F. Being continuous on set F means, it's sort of opposed to the way it's dealt with in Calculus 1, you take an open interval containing x, and we've got that function continuous on that open interval, intersect the domain of the function. The domain at present is capital F. We need to extend G to all of the reals, but we've got the continuity on that closed set. Problem 3.25 says, this is an important one in a probable homework exercise from this section, and we'll use this in the final proof, and the proof of Lusin's theorem in general also. By problem 3.25, G can be extended to a function continuous on all of R. That is, if we've got a function that's continuous on a closed set, it can be extended to a function that's continuous on all of the reals, is the claim. That's exactly what we've got. We've got G is continuous on closed set capital F. The extension guaranteed by problem 3.25 then is a function that's continuous and defined on all of the reals, and it equals function lowercase f on set F. We got it started that way up here. So there's the proposition 311, the lemma we need to prove Lusin's theorem. And Lusin's theorem will liberate ourselves from this simple function stuff. We're going to consider measurable functions in Lusin's theorem. Let f be a real valued measurable function on set E, then the rest of it reads just like that previous proposition. For each epsilon greater than 0, there's a continuous function g on the reals and a closed set capital F contained in E for which f equals g on set capital F and the measure of E set minus capital F is less than epsilon. So before we had simple functions, now we've got real valued measurable functions. Well, we approximated measurable functions with simple functions recently. It was in the previous section. It was a simple approximation theorem. So how about this? Let's approximate the real valued measurable function. Let's approximate it with some simple functions, and then we'll approximate the simple functions with continuous functions. Kind of piece it together. It sounds like an epsilon over 2 proof. In a sense it is. It's a little more involved than that, but that's kind of a big picture idea. Remember, we're going to use Egoroff's theorem, and that dealt with uniform convergence. So let's get into it first by saying, I tell you what, let's take care of the case where E has infinite measure. Let's take care of that with an exercise. And let's consider the case where E has finite measure. All right, and we're going to need that because we're going to apply Egoroff's theorem. And Egoroff's theorem required the finite additivity. That problem from the book is based on this special case result here for finite measure sets, actually. But the finite case is the bulk of the work in showing this in general. Okay. Why, the simple approximation theorem guaranteed us a sequence, f sub n, of simple functions defined on E that converges to F pointwise on set E. Simple approximation lemma let us get close to measurable functions. Simple approximation theorem let us write those measurable functions as pointwise limits of a sequence of simple functions. So the lemma got us close to measurable functions with simple functions. The theorem, simple approximation theorem, creates a sequence of simple functions that converges pointwise to function f. All right, we're in business here if we can talk about simple functions, because that's what the previous result considered, was simple functions and finding continuous functions and so forth. Let n be a natural number. That previous proposition told us that there's a continuous function g sub n defined on the reals and a closed set f sub n contained in set E, for which f sub n equals g sub n on f sub n, capital F sub n, and the measure of the set difference is less than a positive number. Let's take that positive number to be epsilon over 2 to the n plus 1. Okay, now what we've done here is we've applied the proposition to simple function f sub n. So we're replacing the f in the proposition with an f sub n here, and we're replacing the epsilon they had with this quantity here. So, hey, f sub n is simple. So I know I can approximate it in this sense with a continuous function g sub n. There's a g sub n that's continuous and defined on the reals, where we get the equality on this closed subset, and the closed subset is close in size to the domain, capital E. All right, so let's see, we're looking at sequences of functions here. Egoroff's theorem dealt with uniform convergence. More of that, why that's desirable here shortly. But first, Egoroff's theorem, and by the way, that required the finite measure, and we're considering the case for finite measure. By Egoroff's theorem, there's a closed set f sub 0 contained in E, such that this sequence of simple functions converges to f uniformly on f sub 0, and the measure of E set minus f sub 0 is less than epsilon over 2 this time. Okay, and you know there's some epsilon over 2 argument coming pretty soon, but this one's a touch more involved because we introduced this sequence. Define set capital F to be the intersection from n equals 0 to infinity of f sub n. All right, 1 to infinity, that's the sets we defined up here, where we started with natural number n. In the Royden-Fitzpatrick book, 0 is not a natural number. 1 is the loneliest number, the smallest natural number. So 0 is not a natural number. It wasn't included up there. And f sub 0 is where we have the uniform convergence. So when we take the set capital F to be the intersection of all these, first, I'm worried about the size of set capital F. We'll take care of it. And all sorts of good stuff happens on capital F. All of this stuff happens. The f sub n equals g sub n. All this kind of thing happens on the intersection of all these f sub n's. And we've got uniform convergence on f because it includes f sub 0. Now, why so hung up on uniform convergence? The one result you may recall concerning uniform convergence from senior level analysis is if a sequence of functions converges uniformly to a function, and each of those sequence functions is continuous, then the limit function is continuous. A pointwise limit of continuous functions may not be continuous, but a uniform limit of continuous functions is continuous. Here's where we are. We got a bunch of g sub n's that are continuous. We want a single function g that's continuous and defined on the reals. Well, how about we take g to be the limit of these g sub n's? These g sub n's are continuous g sub n's defined on the reals. So let's take these g sub n's, take a limit of them. They're continuous, and we've got uniform convergence. When you've got uniform convergence of a sequence of continuous functions, the limit function is continuous. So that's why uniform convergence is drug into the conversation. All right, about the measure of E set minus F, we define F to be the intersection of all those F sub n's. De Morgan it again, something along these lines. We probably don't have disjointness this time, but we still got subadditivity. the union from n equals 0 to infinity of E set minus F sub n. Let's peel the n equals 0 case off first. We've kind of dealt with it separately. And then we get all the others from n equals 1 to infinity. Subadditivity would tell you this is less than or equal to this measure plus that measure. Here, I'll apply subadditivity to this countable union. And what we get is less than, strictly less than, because I know the measure of E set minus F was less than epsilon over 2. We had the measure of this union was strictly less than epsilon over 2 to the n plus 1 for each n. So sum those up. So countable subadditivity is in the mix. I guess I skipped that step technically. We've got a strict inequality because the epsilon stuff has entered the conversation. We've got an epsilon over 2 from this set. These sets, we had epsilon over 2 to the n plus 1, n equals 1 to infinity, geometric series with ratio 1/2. Sum that geometric series, you'll get epsilon over 2. So epsilon over 2 plus epsilon over 2 equals epsilon. We got the measure of E set minus F is less than epsilon. That we wanted. We still don't have, we don't have the function G. All right. F is closed. We defined it as the intersection of the F sub 0 and all the other F sub n's, and each of those were closed. Countable intersection of closed sets is closed. Arbitrary intersection of closed sets is closed. We got countable. We're in a sigma algebra, by the way, as well. So measurables, part of the story. Each lowercase f sub n was continuous on F. Hey, F is a subset of F sub n. Lowercase f sub n equals G sub n on capital F sub n. We had G sub n continuous on all of the reals. You know, F sub n converges to F uniformly. That's where Egoroff's theorem came in. On set F, we had uniform convergence on F sub 0, and this is a subset of F sub 0. Uniform convergence holds on big sets, it holds on subsets. So we've got F sub n converging uniformly to F, on F sub 0. That's how F sub 0 was chosen. We get the uniform convergence on F itself. You know, the uniform limit of continuous functions is continuous. That result right there. So that's the reason uniform continuity came into the story. That's the reason we did Littlewood's third principle before we did Littlewood's second principle as well. So if we look at the restriction of lowercase f to set capital F, that's continuous. Then we've got little f being, as we defined it here, the limit of the f sub n's is a continuous function on set capital F, but we wanted a continuous function on all the reals. Fret not. Problem 3.25 comes to the rescue again. And this function, lowercase f, can be extended to a continuous function G, defined on all of the reals where G and F are the same on set capital F. So function G is the function you wanted. It equals F, the limit value. The limit function of that sequence of functions we introduced. And let's see, G is continuous on all of the reals that we needed. The only place we don't have the equality is off of set F, that is on E set minus F, and the measure of that set less than epsilon. And that's what we were looking for in Lusin's theorem. So that takes care of Littlewood's three principles. Actually, we'll require these in some of the stuff we do in chapter 4 when we develop Lebesgue integration. But we're good to go. We got measurable functions laid out as to what a measurable function is. We know a few properties of measurable functions. You know, pointwise limits of measurable functions are measurable. For example, we can approximate measurable functions with simple functions. In a sense, we've got this nearly behavior from Littlewood's three principles. So it's time to move into chapter 4 and start the integration stuff. So I'll see you in section 4.1. We'll do a super brief little review of Riemann integration, and then we'll get started on the Lebesgue integration full time. Have a nice day.